All right, well, good morning, everyone. My name is Janie Montblanc, and with me is our co-coordinator, Corey Gooker. And on behalf of the Great Basin Fire Science Exchange and our partners, I'd like to welcome you to this webinar titled Science-Based Guidelines for Safe Application of Vegetation Maps Derived from Satellite Imagery. Cara Applestein, Jake Price, and Matt Germino are our presenters today from the US Geological Survey. And before we start, I'll go over some webinar details. We're using Zoom webinar as our platform. So you'll have both the Q&A box and the chat box, but I think you have to go to your little three dots that say more below to get your chat box to show up. And you can put questions in either one of those. So those should both be available to you. But I think with the chat box you have to use if you want other people, the other attendees in the webinar to see what you said. And make sure that if you do want everyone to see your comments or questions, then go to your chat box and in the to section, click the drop-down menu that says everyone if it doesn't already say everyone. Let's see. So let's see, did that take care of all that? Yes, I think so. Yeah, we'll be using the chat for questions, but we will see questions in the Q&A as well. Please type in your questions at any time and I'll field them to the speakers after the presentations. Okay, now I'd like to welcome our presenters. Cara Applestein is a quantitative ecologist who works closely with land managers and scientists to provide predictive models useful for understanding the efficacy of restoration practices. Her current research focuses on understanding weather effects on post-fire vegetation recovery, mechanisms of invasion, and the utility of remote sensing products for land management decisions. Jake Price is an ecologist whose research focuses on how fuels and fire interact at the landscape level in sagebrush steppe systems. And Matt Germino is a supervisory research ecologist interested in plant-soil environment relationships. His research focuses on post-fire rehabilitation and restoration, invasive species, and integrating science and adaptive land management in forests and rangelands. Welcome all of you, and thank you for presenting today.
Well, thank you very much, Jeanne, and thanks everybody for attending. So vegetation maps are about the most basic data needed for management study of upland landscapes. And yet these maps are surprisingly hard to generate in the mixed shrub steppe that dominates the Great Basin and many other areas of the world. Let's see if I can get this to advance.
Matt, can I interrupt for a second and ask you to put your screen on full presentation mode?
Okay.
Is it all right?
Can you see anything at all?
I do, I see it. Corey, can you tell me, is it on presentation mode?
Yeah, it is. It's fine.
Okay, sorry to interrupt you, Matt. Go for it.
That's okay. That's okay. Now I'll see if I can actually advance the slides. Oh, we can. Good. We're good. Interesting. And so anyways, why is mapping so challenging? The areas of concern are vast, remote, they're hardly field inventory, and to make mapping even harder, they often have important ecosystem variability that's not easy to discern. And sagebrush steppe with the Great Basin is a great example of this problem. Let's see, a little bit of an issue here. Oddly, PowerPoint is showing up in two ways on my screen.
It looks good to us.
Okay.
And we see your pointer.
Yeah. All right, we're going to be showing two PowerPoints on my end. I don't know how this happened. Anyways, so sagebrush steppe is a great example of these challenges. And like most rangelands, there's very little biomass and therefore lots of background soil noise that makes detecting the satellite sensor signal a little bit more problematic. And then to add to this, plants are slow growing, and oftentimes we want to know without small percent changes in vegetation. So one of our principal concerns in the shrub steppe of the Great Basin is the grass fire cycle. And this is a problem because usually we need to know something about both the post-fire vegetation in order to have effective restoration, to know whether or not restoration is successful. And oftentimes we need to know something about pre-fire vegetation. And rarely do we have the field monitoring data available to us. And therefore, whether or not we can get that information from models derived from satellite imagery is a really relevant thing that we need to be worried about. So some of the other issues are resolution. There's practical limits. Temporal, spatially, we have issues with the imagery coming in 30-meter pixels. Oftentimes, the underlying satellites, such as LandCart, might fly at bi-weekly intervals. However, the models are generally only providing information on vegetation on an annual timescale. And these are things that we need to consider, especially when we're trying to compare the vegetation models to field data, which may or may not be collected concurrent with the imagery. So key questions. What is the suitable application given all of these prospects and challenges? And a key problem with knowing the application is knowing something about accuracy. The challenge with accuracy is creating a fair comparison in terms of the benchmark field data that we can collect here on the surface of the Earth and the way that the satellite sees the Earth. So if the satellite is seeing 30 by 30 meter pixels and generating a single value of vegetation or spectrum for that pixel, we need the field data to be comparable. And obviously, it's nearly impossible for us to measure vegetation on Earth exactly as the satellite sees it. And so some of these nuances we'll talk about today. Interesting. Some of the information that we'll present today comes from, or actually all the information we'll present today comes from these publications shown here. The first three publications listed directly assess accuracy. And also we have 5 other studies here in which we applied the vegetation maps for various things, such as generating sampling effort curves to guide field sampling, trying to understand how sagebrush are recovering after fire, using the information to model fires, to simulate historic megafires across large landscapes, or evaluating how well the published information on carbon in the Great Basin extrapolates across space. So the data that we're going to focus on is landfire, the former National Land Cover Database, now known as the Rangeland Condition Mountain Assessment, RCMAP, RAP, the Rangeland Assessment Platform, and LandCart. All of these are derived from Landsat imagery, and some of them use some of the same neural network algorithm to translate or transfer the imagery into estimates of plant cover. Now, I mentioned that there's challenges in getting field data to match the scale at which the satellite sensor sees the Earth. We're very lucky to have a few landscapes in which there's a high density of sampling plots, such as the Soda wildfire, where for about 180,000 of the 300,000 acre area, we've got 2,000 sampling plots. And that means that there's not multiple plots per pixel. However, there's such a high density of points, we can create models, field-based models of vegetation cover that can then be compared with the satellite imagery. So we'll talk a little bit more about the soda wildfire. This is also a burn area that we have done lots of ecological studies on. I think it's about the best well-studied burned area in the world, actually. And it's also a very worthwhile test landscape because there's useful environmental variability, such as here you can see strong gradients in elevation. Sagebrush steppe meets its lowest elevation limits here in the northeast portion. There's many different soil types and lots of very relevant management and natural variability occurring in this landscape. So an ideal test bed that we're going to talk a bunch about today. Okay, I'll pass it on to Cara.
So the next couple studies and slides I'm going to talk about come from kind of a lot of our work where we wanted to utilize remote sensing data where we did not have field data available. And in order to do that, we really needed to ask how we could use this and how well it worked on our studied landscapes. So we initially got into this with looking at post-fire sagebrush and trying to understand how well the NLCD, which is now it's called RCMAP, but back then it was called NLCD, how well that was detecting sagebrush recovery on large mega fire areas in the Great Basin. And part of this was sort of a precursor to additional work that we did, trying to understand how weather affects sagebrush recovery at a very large scale. So we needed to do some validation before we could actually do that study. And we looked at 8 different fires in the northern Great Basin, across which we had sagebrush density and cover. This data came from a number of different projects, and it's all field data. So,
sorry, a little bit of an issue with PowerPoint here.
So this is the linear regression, the comparison between our field estimates of sagebrush cover and then the NLCD sagebrush cover. The red line would show a 1-to-1 correspondence. So if there was exact agreement between these two data sets, it would match that red line. What we actually see happening is the blue line there. So pretty low correspondence between the field data and the NLCD sagebrush cover. And of particular note here is that areas in the landscape where there was absolutely no sagebrush found in the field estimates, NLCD on average would say there's 6.5% sagebrush cover. So that previous figure was just showing a conglomeration of all points in time, but we're also interested in seeing the trajectory of how sagebrush recovery would turn out if you looked at NLCD estimates over time. So we split up our different fires into seeded and unseeded areas and looked at the sagebrush recovery trajectories over time. And we were kind of interested in knowing when that regeneration signal would level out. So the blue line here is a change point detection test statistic, Child's F statistic, which is basically the probability that that point in time is a change in the rate of how fast sagebrush is recovering. And so we can see that a lot of those change points tended to be around 4 to 6 years after fire. So that's the point at which NLCD was estimating sagebrush was leveling out and returning pretty close to pre-fire levels. And when we actually looked at the field data for these points, so those are shown in the stars on Buffalo, 2 different Buffalo plots and the Charleston plots. You can see that the field data was showing very low sagebrush cover at these points after fire, where NLCD was estimating that the cover had returned to nearly pre-fire rates. So the natural next step for this work was to test other products and other functional groups. And this was the first paper where we did intensive validation of both RAP and RCMAP. NLCD had switched over to RCMAP at this point. And we utilized test data from the soda wildfire that Matt had talked about before. I'm going to just show RAP here. We have a whole bunch of different graphs for different years and also for RCMAP. but the patterns that we see in these graphs hold pretty similarly for other years and also for RCMAP. So here we can see that we have a very similar pattern to what was happening with the sagebrush, where areas that the field data said there was absolutely no cover at all, that RAP was tending to estimate those as having a decent amount of cover. But then because we actually have some functional groups where we do have high cover for some things like annular herbaceous or bare ground, we can see that there's an opposite thing happening at the higher range, where RAP is tending to underestimate parts of the landscape where they're actually really high cover. This is what we call the false moderating effect. So it's where either extreme low or high cover values are somewhat washed out by that satellite derived data. And the models are tending to estimate cover as kind of in a moderate range of values, even though in the field we're finding they're either very low or very high. So this was the second paper we did, kind of just following up on the same analysis where we were looking at LandCart. And LandCart is a more recent product, very similar to RAP and RCMAP. It does have a few categories which are more specific. So instead of just having perennial herbs all combined together, there's actually perennial for perennial grasses, annual for annual grasses. So we're able to look at some of those categories specifically. And we found pretty much the same patterns happening here with LandCart as with RAP and RCMAP. So again, that false moderating effect. Some of these functional groups are almost flat lines. So you can see that LandCart kind of estimates those cover values all within a pretty tight range, even though we found a whole range of values over the test field data from 0 to 80% cover. So all of these products are frequently undergoing mini updates, and already we're to version 5 with RCMAP and to version 3 with RAP. So this is the models have been updated. There's been some corrections added. They've changed some of the data sources. So from Landsat, better corrected Landsat data. And we looked at whether there was an increase in accuracy between the two different versions of, so this is just looking at version 2 and version 1 of both RAP and RCMAP. And so the blue bars are showing that there is an improvement in accuracy between the two versions. And then the red bars would show there's a decrease in accuracy. And this is, again, looking at those same SOTA test plots that we had on the previous graphs before. And what we can see for RAP was that there was a pretty substantial increase in accuracy measured by R squared between version 1 and version 2. However, we actually saw some decreases for RCMAP between those two versions. So this was another follow-up where we again looked at versioning. This is in the most recent paper. We looked at the differences between RAP version 2 versus 3 or RCMAP versions 2 versus 5. And what we saw for this comparison was that RAP may have sort of maxed out their accuracy. So there's pretty negligible changes in R squared between the version 2 and 3. We did see some pretty substantial increases in accuracy between versions 2 and 5 for RCMAP. However, it should be noted that on this specific landscape, the study case, RAP was pretty much always a little bit better, a little bit higher in R squared value than RCMAP.
Okay, so we've also tested the accuracy of RAP in support of pre-fire sampling of woody and herbaceous fuels, including cheatgrass and City of Rocks National Reserve and other National Park Service areas in South Central Idaho. At City of Rocks, we estimated vegetation cover at 622 plots with the intention of comparing to RAP's estimates of functional cover. The figures on the right show our field observations from 2023 on the x-axis and RAP's estimates from 2022 on the y-axis for 6 functional groups available from RAP. The solid red lines are trends and the dashed red lines are 1-to-1. And the reason we're seeing RAP's 2022 estimates is because they have yet to release their 2023 product. But even though we're comparing two different points in time, if we focus on some of the more stable functional groups, such as shrubs and trees, we see the relationship that Cara was talking about earlier, but now in a pre-fire context where RAP is overestimating at the lower ends of plant cover and overestimating, sorry, I have them backwards, overestimating at the lower ends and underestimating higher ends, where these plant functional groups are actually more abundant. So here again at City of Rocks, we also classified fuels on the ground with one of Scott and Bergen's 40 expanded fuel models. So the figure on the right is showing the count of plots on the x-axis classified as a given fuel model on the y. Count of plots on the y-axis classified as a given fuel model on the x-axis, and compares the observed fuel model classifications in purple to land fires estimates in yellow for all field sample locations. And what we saw was an 84% disagreement between our estimates and land fires, largely stemming from land fires overclassification of this fuel model 122. We'll talk about this a little bit more later in the presentation about how this high rate of disagreement affects the subsequent analyses. So land fire, as Matt said, is derived from Landsat and DLM in-field plots and provides publicly available geospatial data needed to run wildfire spread models. Fuels data from land fire include Anderson's original 13 fuel models and Scott and Bergen's expanded 40 fuel models. So the simulations of wildfire spread are important for proactive management of the grass fire cycle. However, simulation outputs are only as good as their inputs. So therefore, it's important that we test these inputs first. And one method commonly used to validate those fire spread model inputs is a comparison simulated to observed fire perimeters. Shown here on the right is our best attempt to recreate the 2015 Soda wildfire using the fire spread model LandMAP with land fires off the shelf inputs. The panels on the top show the spatial layout of fuel models according to land fire, and the bottom panels show the resulting spread of wildfire, where blue is our simulation underestimation, green is our simulation agreement, and red is our simulation overestimation. So we can see that the result was a very poor recreation of the 2015 Soda wildfire. And given that these similar simulations would have been used to support active wildfire suppression during Soda, this degree of underestimation from land fires inputs is rather concerning.
So far, most of what we've talked about has been accuracy, looking at plot-based or basically point-based accuracy, comparing one specific plot on the ground to a pixel in RAP or RCMAP. However, the next question becomes, if we don't see very good agreement at a plot-based scale, is there a larger spatial scale where we could maybe get better agreement between different data sources? So in order to ask this question, we need to create a basis for comparison. And this is not a trivial thing to do, because in order to have a good basis for comparison, you need a continuous map that matches the scale and resolution of the remote distance-based maps. So we created our own field-based map models on the Soda wildfire using up to 2,000 plots per year. We did an empirical Bayesian frigging regression, which is kind of a combination between frigging and regression, and created plant cover maps that match the functional groups that RAP and RCMAP LandCart offer. One thing to note here is that the training point data that we used to create these maps was actually a completely different data set than the test data that we utilized to assess accuracy. So we showed those graphs back previously in the presentation. So those test data were completely different from the training point locations. And because of that, we were able to assess accuracy on our own maps too, using a completely different set of data. And we found that our field-based maps generally have higher R-squared values than the RAP and RCMAP. However, there's a couple of cases in which RAP actually, for some years, some functional groups actually had slightly higher. And so this point just underlines the fact that it's really hard to create models of vegetation cover across such heterogeneous landscapes and have a fair basis for comparison. However, we still think that it's really important to be comparing these field-based sources of data with the remotely sensed-based sources of data, because it's a little bit concerning if you're getting data about plant cover from two different sources and they're not agreeing with each other, that your data would say much different things depending on what your source of data was. So we utilized these maps that we created to look across scales and see if we got better agreement between the field-based models and the satellite-derived models as we increase the scale comparison. So here's what we did. On the left side, what we did was took a bunch of different random sampled polygons across SOTA. So we started from polygons that were very small in scale, and we went up to pretty large scale samples. And we took the average cover of each different functional group within those samples and compared RAP and RCMAP with the field-based maps. And so these are the graphs on the right side that came out from that. You can see the average difference in cover between the field-based map and RAP here, and then that red line is the relative standard error. So what we see is that there's pretty large standard deviation, large relative standard error when you compare these two different models at a pretty small scale. And sorry, I'm missing the x-axis on this, but that is kilometers, radius kilometers. So it's the radius of a circle in kilometers. So as you increase the scale, which you're comparing these two products, the relative standard error generally goes down. So that tells us that if we're looking at fairly large scales, like the size of a megafire, that we can expect to have pretty good agreement between our two different data sources. But there's a lot of variability when we start drilling down to those smaller scales, like plot level, like treatment level, where there's a lot of variability in how these two different models are estimating cover. So one of the things we are interested in knowing is if are there any variables which can help us predict how these models differ? So do we see consistent trends in the agreement between the field-based models and the satellite models if we look over a bunch of different landscape characteristics? And so these graphs are created looking at pasture level differences. So that's kind of a management relevant scale. If you look at the difference between the field-based models and the satellite-derived models. And so we looked across these different landscape characteristics. And again, this is RAP. The relationships for RCMAP are pretty similar to this. But what we see occurring here is that annular herbaceous cover tends to be estimated pretty well at those low elevation areas where there's not a lot of topographic heterogeneity. So kind of low flat areas, annular herbaceous cover tend to be estimated pretty well. There's good agreement between the two different models. However, if you go up in elevation, you start becoming more topographically diverse. There's less agreement between the two models, and RAP tends to overestimate annular herbaceous. The opposite actually occurs with perennial herbaceous, where perennial herbaceous tends to actually be overestimated in those lower elevation areas. And as there's more agreement between the two models once you get up to that higher elevation area where it's a little bit more diverse. And last thing to point out here is that we looked at change over time as well. And this is not quite as strong for RAP. RCMAP actually has a stronger trend here. But one of the things that we saw was that there was less agreement between models right after fire, so the 2016 year. But there was some convergence, a little bit more agreement over time. Once we got out to 5 years post-fire, a lot of the functional groups started to agree a little bit.
So recreating historic wildfires is one of the primary ways to validate fire spread model inputs, but it's also a way to look back and learn from especially catastrophic wildfire events. Problem though is that the quality vegetation and fuels data that we need to recreate historic wildfires typically doesn't exist. Our efforts to inventory landscapes often come after such disturbances. Therefore, remotely sensed vegetation is often the only means available for understanding pre-disturbance landscapes. In this example, potential applications we're referring to our paper. in the top right corner, where we use perhaps vegetation cover estimates to classify our subject landscape into forest vegetation cover types, which were then related to sensible fuel models from the Scott and Bergen expanded 40 fuel model data set, and ultimately used to produce a more accurate recreation of the 2015 solar wildfire and flame map than was possible with land fires off the shelf inputs. So even though we discovered the inaccuracies of RAP was nonetheless useful in determining the spatial alignment of fuels for the target landscape and which fuel models should be used to represent that landscape to generate much more accurate recreation of the wildfire than was possible with nominal off-the-shelf land fire estimates. So earlier we talked about the high rate of disagreement between observed and land fire. Right. Earlier we had talked about the high rates of disagreement between observed and land fire estimated fuel beds at City of Rocks, which was 84%. These two maps here on the left show the spatial distribution of fuel models classified by either land fire or from our field validation efforts, which combine field data and RAP to interpolate fuel models for the landscape. You can already probably see there are some major differences between these two maps, but let's just focus in on the Smoky Mountain area, which is circled here in this dashed red line, which contains some of the City of Rock's oldest and largest pinyon pine at the very northernmost extent of the species range. So it's a very high value resource for the park. If we look at the underlying fuel model classifications, we can see that land fire characterized much of the surface fuels around Smoky Mountain as the shrub 7, which depicts very dense 1.5 to 2 meter tall shrubs. However, our field efforts classify much of the same area as GR1, which is consistent with short sparse grasses. And just so everyone can see what that looks like, here's a photo taken from Smoky Mountain just this last summer, where we see pinyon pine in the background with an understory of short sparse grasses. Now on the far right, we see the resulting fire risk simulations where flame map was either parameterized with land fires inputs or our field and RAP, field plus RAP inputs on the right. The resulting estimates of risk, the resulting estimates of fire risk model simulations using land fire inputs greatly exceeds the more reliable simulations, which use a combination of field data and RAP to provide managers with more reliable information that they need to proactively plan for the future.
This is another application in which we've used RAP. So this is a situation where you don't have any field data and you need to design a field monitoring plan. So in order to know how many plots to put out on a landscape or to estimate how many plots to put out on a landscape to estimate vegetation cover, you need to know something about that landscape to begin with. So there's a circularity problem where if you don't have any information, you can't create the sampling effort curves to determine how many plots you need to monitor. So we've actually used RAP in this situation to create sampling effort curves to decide how many plots to sample. We did this for 11 different fires across the Great Basin that we were looking at to assess post-fire treatment outcomes on. And the top panel graphs here is showing what RAP would estimate for what relative standard error would be based on the number of plots across the landscape. So we utilize these curves to try to determine how many plots were needed for each of these different treatment types to achieve a relative standard error of 20%. However, we can see in the bottom panel here that when we actually went out and did the field monitoring on these plots that we decided upon using RAP, that our actual relative standard error was much higher. So sometimes above 40%. And I think this just underlines again the fact that it goes back to the false moderating effect, where there's actually a lot of heterogeneity on the landscape, which we pick up when we do field monitoring, that RAP does not pick up. So when we improve these these tools for sampling effort in the future will probably take that into account and add some extra noise into RAP in order to estimate how many kiloplots we need.
And of course, that issue would be present with just about any vegetation map derived from satellites. Simply an inescapable outcome of living the landscape of large pixels. So our last application here was a study led by Digger Anthony, who recently transferred over to the Fish and Wildlife Service. He's leading the fire monitoring program for them. And this paper is technically still undergoing assessment, but it's been cleared for dissemination by the U.S. Geological Survey. And we discovered some really interesting value of RAP in light of the inaccuracies that we described today. It can still be a useful predictor of post-fire outcomes. So on the right here, you can see 4 megafires encompassing how many millions of acres? Almost 2 million acres. And a lot of plots are available on them, probably close to 2,000, 2,500, 2,000, a lot of plots. And so for these megafire areas, when a megafire happens, the land managers are faced with, number one, having to do some sort of inventory of this unplanned disturbance. And they need that inventory in order to propose or prescribe their fire response management. What types of activities that might go on in the BLM's emergency stabilization and rehabilitation program, for example. For example, where should they think about applying herbicides or maybe seeding of naturalized or native brush grasses? And obviously in sagebrush steppe, one of the biggest concerns is where are we most likely to see threats of annual grass invasion. So very rarely will there be pre-fire monitoring plots, as we've mentioned already in this talk. And can we use data such as RAP to get an idea of where in the landscape conditions may be before the fire might not have been favorable for a good recovery after the fire. So on the graphs here, you can see the post-fire annual grass abundance that was actually measured in the field underneath all those black marked plots in the maps. And on the x-axis, you can see a variety of predictors, some of which, for example, on the far left is elevation. And here you can see a very strong threshold. Unsurprising to you, at the higher elevations, we observe less annual grass invasion. But we know that pre-fire vegetation conditions are probably really important. And indeed, that middle upright graph here shows the ratio of annual to perennial herbaceous cover estimated FEMA. And the estimate is integrated over 3 years to help us avoid the vagaries of any true wet or dry year, because wet or dry conditions strongly affect the amount of annual cover that's observed in the year. And what you can see is a ratio of around 0.4 for annual to perennial cover. In other words, 4 parts annual grasses or annual herbs to 10 parts perennial cover is a threshold for a post-fire annual grass events. Above that threshold, you see dramatic increases in the abundance of annual grasses with every bit more of our annuals we had before the fire. So strong threshold. That's a really valuable threshold that could be easily mapped across these landscapes. Keeping in mind that when we drill into a megafire, as Cara showed, the resolution error is going to start increasing. Another useful one is just annual herb cover by itself. Here you can see that right around 13–14% annual herb cover before fire is again another threshold. So in light of the inaccuracies, we're observing a number of cases where these data are, number one, the only available information, but number two, can be useful predictors. Okay, next slide, please. Okay, so to wrap up, here's some take-home messages. Hopefully you've seen here that clearly the remotely sensed vegetation maps derived from satellites are best applied to large areas. So as you get to smaller and smaller areas or times for application, your likelihood of error increases. And even going into megafires, you really should take care. You're more likely to not have errors when you're averaging across many megafires, as in the previous slide, or if you're dealing with assessments at eco-regional or state levels. The imagery is, the models tend to be most reliable when you're focusing on dominant plant types, such as annual herbs or perennial grasses, and where are they dominant? So it's, for example, would be annual herbs on relatively low elevation areas, especially in the fire. And we need to take caution where the cover values that you're focusing on are relatively low or relatively high due to this false melody that Cara described. And there again, we're likely to see that the models are overestimated cover when the target points are scarce, such as sagebrush in the fire, or rare species are at their range limits. And conversely, when those cover values are very high, you're likely to underestimate them. This is important because a lot of our management targets relatively low or very high abundances of our species of concern. We are better off to use the imagery focusing on substantial cover variation. In other words, if you're simply looking to make a map where annual herbs are greater than 50% cover or are really scarce, you're probably making a safer application than if you are trying to make a map of, let's say, where cover is less than 5% or more than 5%, especially in a situation where your cover values might only be having a total range of 1 to 10%. Let's say, for example. And then finally, change detection. This one comes up pretty frequently. There's some rationale to think that we may be safer applying imagery in the models to change detection because there's less nuance or introduction of spatial effects. But one thing you need to keep in mind is that the accuracy in terms of the match of the field data and model data to the field data may actually not be consistent in one year to the next. So some consideration of this for safer application. So there's a number of other things that we could talk about that we've gone on now for 40 minutes. And so we're wondering if we have some questions.
Great, thank you all so much. Audience, if you have questions, please type them in either to the chat or Q&A. We'll look at both. And I'll start with the first question. How was field-based vegetation cover estimated for these studies? Could that method affect the correspondence with remotely sensed estimates as well?
The answer is yeah. The latter part of the question is absolutely the style or the technique used to measure vegetation does matter. And we've used some different techniques. We kind of glossed over that just for time saving, but on the soda wildfire, we used on the computer, we used grid point intercept on images that we captured using overhead photography. So we put cameras on top of poles, holding up, capture a 2x3 meter area on 2 plots, 2 images per plot, and then we would determine the abundance of vegetation underneath about 100 plants for each of those 6 meter square areas. So key point, in that method, the area measured for each field point is considerably smaller than pixel, what I was with. But note that in some of our more important analyses, we took those field data and created a landscape level model for which we have estimates of 30 by 30 meters. And similarly, for Jake and your work, we use different method.
Yeah, we used 13-meter radius plots that were supposedly aligned with pixel centers.
So about the same exact size.
Pretty close to a 30 by 30 meter pixel, and then like I said, we tried to align them with those pixel centers so we would have more good comparison. And once that wrap 20 by 3 product comes out, you can validate that.
So there are, on one hand, we've got an assessment at each point, which is at the scale of the pixel. But of course, the audience is wanting to know like how well can we be assured that a field plot actually does align with several pixel.
There's always going to be 5 to 10 meters of error when you're in the field located in this pixel center.
Yeah, but the inference is drawn over, in this case, on the order of like 1,000 fish pixels. Right, so
I think one other thing to note, which is when you're doing monitoring, it is important to think about the ecological or biological scale of your target metric. And if you're talking about sagebrush plants, for instance, so we've just shown cover here. We've also done density for sagebrush as well. And I think one really important thing to think about is a lot of objectives for sagebrush is set by density. And one figure I didn't show for the NLCD comparison was that there's a really large range of sagebrush density that occurs under 1% cover. So you might have 1% cover and have a huge range of densities. And those densities might actually be meaningful to whether that site recovers or not. So, and it is important to think about when you have a bunch of little sagebrush plants, actually monitoring a smaller scale plot might tell you a little bit more if you doing a bunch of those versus averaging over a whole pixel size, where those couple little plants that are there are going to be pretty much just washed out.
and then I'm trying to remember if we have any style monitoring.
So there's, for the accuracy assessments, no. There was a couple studies we can about here where we did have style monitoring. So
which would be 3 50-meter transects,
25 meters.
25 meter, in our case, 25-meter transects that would radiate out from exposed from the central point. So for those, we do have field plots that are approximately the same scale.
Yeah, and it should be noted that RAP and RCMAP were created or classified using the data that was at that scale.
Okay, thank you so much. The next question, for the number of plots needed for a given standard error estimate, what is the study size area that you were considering?
Yeah, it varies. So a lot of these we have done on treatment that are typically in the range of 2,000 to 10,000 acres. Specific treatments within a fire. We have done this for pasture levels too, which again, probably kind of in a similar range of 2,000 to 10,000 acres. I think for some of Jake's work on City of Rocks, they just did it across the whole area, right? Yeah, across the whole area. So that the sampling ever curves can really be scaled to whatever the area is. And I think one of the nice things about that is that it's not just automatically larger area needs more plots. It's larger area that is more heterogeneous, probably needs more plots. But it could be a small area that's heterogeneous, need the same amount of plots as say a flat area with a bunch of cheatgrass that doesn't have a lot of energy.
And by the way, some of the publications that have been made available to you actually have models, predictive models for what Claire is describing right now that could be used to help estimate how much something you're doing, right?
I'll put a plug out there that I actually have a project ongoing that hopefully if it gets funded will be out in the next year or so. that is going to be a toolbox for managers to use to estimate the number of plots they need on landscape, given a whole bunch of different customization things that can go in.
In the meantime, one of the components of this larger tool that Cara is describing was just created. It's called sample range, and a publication on it describing it just came out a couple days ago, I think, in Electronic Project Management. And that's a relatively easy tool to use.
Great, thank you. Next question, what was the spatial resolution or grain size of your field plot-based cover estimates?
It was about, I think we did 10 by 10 meter pixels because I noted that there was prigging and regression component to it. So the regression component, we actually utilized elevation and heat load information as well to help kind of help classify the maps. And the heat load that we took into it was about a 10 meter by 10 meter pixel. So that's the scale at which they were initially created. We did match the scale to 30 by 30 meter pixel for comparison with rapid RCMAP.
Great, thank you. And Cara, when you can you scoot a little bit closer to the mic when you answer questions? Thanks. Next question, have you quantified the variance of your field-based cover estimates?
So that was actually one of the graphs that we showed. So that's the relative standard error. There's different ways of doing variance, but this is one way.
Just probably describe what the standard error is.
Yeah. So relative standard error is the standard error of the estimates divided by the mean. So if you had a really, really low mean, but relatively high standard error, your relative standard error would be high. So it's basically allowing more error to exist if your estimate, the higher your estimates are. So we did, so the bottom graph panel here in this figure is actually showing the relative standard error for the field data we collected. So doing the same sort of simulation where we look over the number of plots sampled. And I think one of the takeaways from this, which will probably go into some of these tools that we're creating, that 20% relative standard error that we sort of decided on a priori came from McCune and Grace, a book on ecological monitoring, where they say that 20% relative standard errors is an achievable or reasonable standard for ecological research. And I think what we would probably say based on our field data is that that is a very, very high standard, which most people are probably not going to achieve. And so kind of thinking about maybe more in that 30 to 50% relative standard error is achievable with not a huge number of plots. Like in some of these areas, you know, this is on one specific fire that we're looking at, but we had 8 plots for this herbicide treatment in 2017 in that middle panel. And we can see that with, so this is showing cheatgrass, exotic annual grass, and exotic annual grass, perennial grass, and sagebrush. And we can see that for exotic annual grass, we're getting pretty close to that 30% range. The sagebrush and perennial bunch grass is higher. Sagebrush after fire is just really patchy. It's probably gonna be pretty hard to get an estimate that doesn't have a lot of variability to it.
Great, thank you so much. 2 more questions it looks like. I would love to take another look at this slide, at the slide comparing RAP pre-fire functional group values to plot-based post-fire measurements of annual grass. I'm very curious about the potential thresholds of 0.4 ratio of annual perennial herbs and 14% cover of annual herbs.
Yeah, this is powerful. It's this is just so everybody knows, this is a pretty strong model. Like this, statistically, this is sound. It's based off of a lot of points and high quality field data. And so this is useful. I would think that, well, let's say this, let me put it this way, in terms of my confidence level on this. If I were on a bear team or an ESR project and we had a 500,000 acre megafire, I think I would probably take the RAP data and map out this ratio, and I would create it. I would specifically mask out the areas that are below 0.4 and above that ratio of about 2. You know, would probably put a grayscale on those values to basically highlight the areas where we are greatest risk of seeing an increase in annual grasses after fire. So basically what this is telling us is that for every little bit more annual grass you get above the 0.4 annual to perennial ratio, you're likely to see you're likely to see an increase in annual grasses. You're likely to see annual grasses becoming more and more abundant. Actually, let's take a look at that y-axis here too. So this is relevant. The effect size, we're starting out 24 and going to 36. I should point out that for many management concerns, a threshold of concern is 20% annual grass cover. So here you see the annual grasses marching up above that threshold. That scale, by the way, doesn't go from 20 to 70% cover. It's definitely a much more modest range, but it just shows that there is historically across these 2 million acres that there's been a pretty strong signal where you're having a positive relationship of more annual grasses relative to perennials before the fire, more invasion. And by the way, one of the implications of this is that if you combine these ratios with the absolute cover amounts, it means that if you want to manage these landscapes for better resistance and resilience post-fire, you kind of need to have a lot of perennial grass cover. David's estimates was on average in the paper I didn't describe this as having at least like 30% perennial cover. Yeah, so
It is all herbaceous cover, so it could be forests in addition to the
herbs. Yeah, forests plus grasses.
Okay, thank you. And the last question, have you thought about also providing managers with guidance on safe application of field-based plot data? There are many known biases in field data collection and challenges with scaling up, as you pointed out.
Yeah, for sure. We emphasized that in one of the recent papers on this. The answer is yes, we definitely are concerned about that. And I suppose one of the challenges with doing that is that there's such a wide variety of field data types. But for sure, actually at the moment we happen to be working on a document of an assessment of metrics for evaluating post-fire seeding effects. And this theme is one of the major chapters, if you will, in that document. So yeah, sure. But yeah, so the point there is that we try to emphasize this right off the bat, that the problem is that there really is no true benchmark. Like we can think of field data as being, the absolute well-known benchmark, but that's actually not the case. there really is, I mean, presence absence of vegetation types is about the only thing we can really know. Cover is extremely hard to estimate even in the field. And if you choose one method or you apply that given method with a little bit something a little bit different about it, you can actually generate considerable variability. How you roll cover estimates out from plots to a larger landscape also, I mean, basically now you're doing modeling, and so you're introducing model error. So I think the point that everyone needs to keep in mind here is that while yes, we can use high density models created from high density of field plots as something of a benchmark, there are imperfections in those estimates. They are just estimates. They're models. What's the physical thing?
No model is correct, but some models are useful.
Ground truthing is a misnomer. Thanks for your insights and work.
Yeah.
So it is the top of the hour for those that have to jump off. We'll follow up with the video and please answer our 3-question survey when I close the webinar. But if you guys can stay on for 1 more minute, there was a clarification on one of the past questions, and it was interest in the accuracy of the plot data. Cover at a field plot is estimated with error, and he was interested in whether anything is known about how large those errors are.
Well, yes, we've done a variety of error assessments. Calibration. From one observer to another observer. And gosh, we've done some other ways too. We've looked at different techniques. They're associated with choosing one technique or another.
You guys are a little bit quiet.
Oh, sorry. We don't have like an off-the-cuff error estimate to answer that question.
I guess what would be the best? So we have calibration data, which is basically all the information that we're doing. So for SOTA, we had specific calibration plots where we had different teams go out. So we do know something about observer error between different teams for those calibration plots. For the ESR extensive data, which we're now collecting, that
project, by the way, seeks to take the high density plot approach we use for SOTA and apply that to many other wildfires.
Yeah.
But the error estimate, we would say an approximate range of errors that we see.
Well, for the ESR extensive, I mean, you have to be within 10% cover every region.
Okay, and that's a nominal guideline from Bureau of Land Management. Yeah. So, so you could have a situation where you have up to 10% error between different measures. Generally, I think we're well aware of that.
Great. Thanks for sticking on to answer that question. All right. Well, thank you all for the wonderful questions, and thank you so much, presenters. As I mentioned, we'll follow up with the webinar. I think hopefully I think the Zoom is supposed to send an automatic link to that video. So we'll follow up with that. And there's a 3-question survey after this webinar. And again, I appreciate everyone's time. Thank you all. Thanks, Matt, Cara, and Jake. Have a great rest of your day. All right. Bye.
Bye.